So let's continue with the second part of our lecture, where we ended up with, during the first part, was looking at the notion of an interaction graph. Sometimes it's also called the connectivity graph of a set of factors. And here's the example. We had these 5 factors, and this is the interaction or connectivity graph for them. And the task was, I give you this graph, and then I hide the CPTs from you, or the factors, and I tell you, here's the variable order I'm going to use. What would be its width when used in the context of variable elimination? And once more, what is the interaction graph? The interaction graph is obtained by including a node for every variable that appears in a factor. And whenever we have a number of variables that appear in the factor, like in this case B, C, D, we pairwise connect them. So I'm going to flash now the sequence of graphs from this example and ask you to discover the pattern. Look what we did. Earlier we did the symbolic simulation, right? Here's the symbolic simulation, correct? And look what happened here. There was the set of factors we started with and how it was changing, correct? Until we eventually got the factor over E. Now, what I'm going to show you next is the interaction graph that corresponds to each one of these set of factors. The one we looked at was for the original set of factors. But now I'm going to show you the one for this set, and then this set and that set. Okay, and maybe from there you infer the answer to the question that I posed. Right? Here's what we started with, S1, that's the interaction graph. When I eliminated what? The variable B, right? I got this set of factors, correct? That's the interaction graph. Here's CA, there is an edge between CA, EC, there is an edge, and then you have the factor ACD. I must have a clique over these, and so on. Now, I eliminate one more variable, and then I get these set of factors, and here's the interaction graph, and da, da, da. Now, the question for you is, if I just give you this guy, and I tell you generate that sequence of graphs, can you do it? The goal eventually is to find the width of the order. So yes, we're starting with this guy. I'm eliminating the variable B. What do I do to generate this guy? Connect all neighbors of B. Make sure they are pairwise connected, and then delete B from the graph. Once more, to eliminate B from this graph, pairwise connect all of its neighbors, and then remove B. In this case, the neighbors of B are A, C, and D. They're almost fully connected, except that an edge between A and D is missing. And then I add it, and then remove B. What's the reasoning? The reasoning, when you remove B from the set of factors, you have to multiply all factors that mention B. That new factor you're constructing will include all neighbors. So it must pairwise connect them in this guy. That's basically it. Give you the original graph, you do the elimination process. This is a well-known elimination process in graph theory. Give you a graph, give you a variable order, and you do this elimination, generating these graphs. Now, the second part of the question is, then what is the order? What is the width, sorry, of the variable order? Right. As I'm doing the elimination, anytime I'm eliminating a variable, I look at how many neighbors does it have. And I take the maximum of that. So I do this elimination process that we just described here, and I keep track of the maximum number of neighbors that I see for any eliminated node. And that would be the width of the order. We're good? Okay. Now, this is nice because it tells me something about the complexity of running variable elimination with respect to a particular order. But our main objective would be, how do I choose a good order to start with? And that's what we're going to do next. What do you guys think? What would be a good heuristic for finding a good variable order? One with small width. So do greedy. Pick up the node that has the smallest number of neighbors and eliminate that first. That is actually known as the min degree heuristic. Let me say that finding an optimal elimination order is actually NP hard. That's difficult. And in fact, you can never beat the tree width. So if a graph has a certain tree width 7, there is no order that has a width less than 7. And moreover, there is an order whose width is 7. So in one way to define tree width, there are multiple definitions for tree width. One way of defining tree width is to say it's the width of the best elimination order for that graph. But let's go back to the min degree heuristic. The min degree heuristic is interesting because of two reasons. It's actually not the best you can do. That's not the state of the art. There's another one, which is somewhat surprising. But this one is actually optimal if the graph happens to have an elimination order of width less than or equal to 2. So for certain kind of graphs, this heuristic is actually optimal. We'll give you the optimal elimination order. Your chapter 8 has a lot about the subject. And if you look at the pseudocode in this case, it's what you would expect, right? Just doing generate the interaction graph from the CPTs and then iterate from 1 to, the number of variables you want to eliminate, and then find me the variable with the smallest number of neighbors. And then number 4, add an edge between every pair of non-adjacent neighbors of the variable I'm eliminating, and then delete the variable. Let me tell you why I'm going over this. Because I want you to try to suggest another heuristic. So this is min degree. There's another heuristic that actually works better than this in practice, and that's what people basically implement. Not this guy, the next guy. Any ideas? I can give you a hint. I can point you to a line in this pseudocode, or I can give you a name. Which one do you want? The line? Okay. This wants to be more challenged. Number 4 is the hint. Yes, go ahead. Exactly. And it is called min-fill heuristic. You instead of eliminating the variable that has the smallest degree, you think about how many edges it will add when I eliminate, and you pick the one that adds the smallest number. And it's called the min-fill heuristic. It is, as I said, kind of the state of the art. It is not as clear why it works. Actually, I did with one of the students a while back an analysis of it. And the best we could do is we showed a large number of situations where the choices that it's making can be provably optimal. Right? You can't prove that it's not optimal, it's heuristic. But there was this notion of here are all of these very common cases where it will eliminate variables that are optimal in the sense that they do not prohibit you from completing the elimination order in an optimal way. So, anyways, it is the algorithm that is of choice. It has other uses beyond this particular one. Folks, we still need to talk about how to handle evidence, and we need to talk a little bit more about tree width to build your intuitions on that. But let me just say that at this particular point, you have enough to go and implement a very serious inference algorithm, exact inference algorithm. Once more, a representation for factors, sum out operation, multiplication operation, and then a heuristic for finding good variable order, and you're in business. You're able actually to get good results based on that. Let's now show you how you can do evidence, because it turns out to be also very easy. Because now we're doing just marginals, but typically you have evidence and you want to compute posterior marginals. And really, it's going to boil down to 2 observations that we're going to make. And then you put them with what we did, and you're there. The first observation is this, and this is an interesting one. The goal here is, I have the variables I want to compute the marginal over, which is like DE. But I also have evidence in this case. A is true and B is false. So what I'm really interested in is this. What is the marginal over Q given the evidence E? And then what you're going to get back is a factor that represents that conditional distribution. So look at this factor now. These numbers are this. For example, if you look at the third row is this guy. D is false, E is false, and I have this number. What does that mean? Look how you read it. You read this row. The probability that D is false and E is true, given this evidence, is that. Okay? Now, here's the interesting observation. And this was made actually, I think, in 88, in a paper by Mark Piot, who was a graduate student at Stanford, and Russ Schachter, who's still faculty there. If this is your goal, it may be a good idea not to compute this, but to compute what we call the joint marginal instead of the conditional marginal. What's the difference? I want to compute Q comma E, Q and E, instead of Q given E. And then this is a marginal distribution. So if you look at the third row, which is D is false and E is true, then really this number is the joint, not given. Now, why is this a better idea? It was put in the context of a certain algorithm at that point, and it was found that doing this is easier. But actually, this, not only easier computationally, as you'll see now, or more convenient, there's another advantage to this over the other guy. Anybody wants to guess? The claim is this guy has more information than the previous guy. Think about it. How is that the case? The joint marginal has more information than the conditional, which means I can give you the other guy from this, but I can give you even more. Someone said probability of evidence. Look what happens if you add up these guys. If you add up these 4 rows, what do you get? You get the property of E, which is the normalizing constant. You divide every row by that, you get the conditional, but I also gave you, as a side effect, the property of E. You can't get the property of E from the other guy. So it is actually a good idea to do this, and to see why, look what you're doing. When you're adding up these rows, you're evaluating this equation. You're summing over all possible values of Q, then you're going to get this. So I'm giving you back this probability of evidence. Once more, you normalize, you get the conditional distribution. Okay, this was the first observation. And now the second observation. And then you're ready to do evidence and compute conditional marginals or posterior marginals. This observation is based on a new operation on factors that we're going to call reduction. That is, I give you a factor, and I give you a piece of evidence, E, and I say reduce the factor by that evidence. And it's pretty simple. Let's look at it pictorially and then the equation. Here's the factor over dE. Here's the numbers. Here's the evidence. What does it mean to reduce the factor by this evidence? Very simple. You zero out the rows that conflict with the evidence. Plain and simple. E is true, then the second row and the last row gets zeroed out. You leave everything else intact. Good? And here's what the equation says. This is the notation. We're now doing F and then putting E as a superscript. It is the same if that row is consistent with the evidence, it's 0 otherwise. All right, now, here's the observation. It's coming on the next slide, but what this slide is saying is that we will adopt a convention next where we are going to suppress the 0 rows. So we avoid, make them more compact. So something like this will be written like this. So the guys that are missing assume that they are zeroed out. All right, here's the key thing. Look at the first equation. We've seen this when we did marginals. Now I'm telling you, I want to compute the joint marginal over variables Q and the evidence E. Just like before, I want to eliminate the variables A, B, C, which are the variables other than Q, but I do it on the joint after reducing it by the evidence. I think you should be able to see that. That is, take the joint, the big table, zero out every row that conflicts with the evidence, and then do your elimination. You should get this guy. I still have to prove it, but it shouldn't be. It should be believable, right? This is exactly what we did before. If you take the E out from here and take E out from there. Now, the main observation is this. If you have two factors that you're multiplying and then reducing, then you can reduce them first and then multiply them. So I can write this as that. Now we're in business. Correct? So what is this saying? Saying it's the same. Just before you start, reduce every factor and just go on. Do your usual business. Let's look at an example. We did this example before without evidence. These are the three factors. The evidence now is that A is true, and I want to compute the joint. So I want to compute the probability, the distribution over C and A being true. So what do? I have to reduce. What happens here? Second row zeroes out. What happens here? Two rows will zero out, the last two. That's basically it. And then what we did before. Here are the factors after they've been reduced. Look at this guy. Lost one of its rows. This guy lost two, and this guy stayed as is. We've seen how this works. I'm doing this. I'm summing out A, then B. And look what the difference is now. I'm working with the reduced guys. We've done this before, right? And here it is. Here are all of the intermediate factors. Multiply, sum out, multiply again, sum out again, da. If I add up these two numbers, what do I get? Probability of the evidence that A is true. And I normalize, and I got you the posterior marginal. Beautiful. Right? By the way, historically, this algorithm appeared last. So it is the simplest of everything we're going to do. But that's not the order. This was early 90s. People started doing algorithms in the 80s. So there was UDA's conditioning algorithms and polytree, and there was something called the joint tree, which is kind of the more sophisticated version of variable elimination. And in the 90s, people came up with this simple explanation of things. So we're starting with it, but it was the last. It was quite difficult. There was a time where the number of people that knew about doing inference in these graphical models was relatively simple. And people worked hard to actually come up with this beautiful semantics and simple explanation of this principle. Okay, this is the pseudocode, very similar to the previous one. That's VE PR2. The only difference really is this, that now we're actually reducing, but pretty much is the same. And now we have really two more segments, relatively short, and depending on time, we may do the last bit as well, a very also short segment to finish this particular chapter. The current segment is we're going to just say a little bit more about treewidth to just further the intuition about this notion. We've already mentioned it a number of times as a number that applies to a graph and that measures its tree likeness. And here, let me say something because it can be confusing. In the literature in graph theory, the notion of treewidth is a property of an undirected graph. Right? So I give you an undirected graph and I tell you what's the treewidth of this guy and say it's 1, 2, 3, 7, and so on. In our case, we'll typically talk about a Bayesian network. Say, what's the treewidth of the Bayesian network? That's a directed graph, right? The intention here is when I tell you what is the treewidth of a Bayesian network that's DAG, I'm talking about the connectivity graph of its CPTs. That's the intention, right? So literally, it is not the treewidth of that DAG. It is the underlying undirected graph. And the one way you can do this is to look at the interaction graph, to look at the Bayesian network. If you look at the Bayesian network, we can guess what the CPTs are, right? So it's every node and its parents. And then you can say, what's the interaction graph of that of those CPTs. But there is a more direct way of doing it, and let me show you this visually here. If I show you this guy, and I say the tree width is 3. So as I said, what I mean is the 3 is the tree width of the connectivity graph of the CPTs of this network. That you can get easily like this. If you look at a node and its parents, you make sure that you connect all of the parents pairwise, correct? And then you drop the directionality of the edges. That's going to be the same thing as the connectivity graph of the CPTs. And by the way, this process that I just told you, they call it moralization. So you say moralize the DAG, and then you get an undirected graph, and then you talk about its tree width. All right, so I just want to make a few observations on tree width here. One is that, which is we already mentioned, that you can define the tree width as the width of the best elimination order that you can obtain for the graph. The other thing is to look at these concrete examples and see, look at this guy. The claim here is tree width is 1, and the claim here is the tree width is also 1, even though the number of nodes doubled. So it's not about the number of nodes. Look what happened from here to there. We added 1 node only, and tree width went from 1 to 2. Why? Here's a fact about tree width that you should know. Right? The tree width can never be less than the number of parents that a node has. That is a lower bound. If you have a node that has 2 parents, tree width cannot be less than 2. You have a node that has k parents, tree width cannot be less than k. And that's what happened here. The node I added, right, made this guy have 2 parents. So that actually, okay, look what happens here. I added some more loops. Tree width is 3. I added more loops, but tree width is still 3. So tree width is not exactly a function of the number of loops. It's a little bit more. We will know more about it later when we talk about the next inference algorithm. But for now, I want you to know this, that the number of parents per node is a lower bound on tree width. Trees have tree width of 1. This is a tree that you know for sure, just 1. This is also a tree, by the way, just drawn in a funny way. Do you remember what we called this guy? We had a name for these guys. Tree is every node has a single, at most 1 parent, right? What is this guy? Polytree, correct? It's still a tree in the sense that you don't have loops, right? But it's not a tree because some nodes may have more than 1 parent. What did we say about the tree width of the polytree? It's precisely the largest number of parents. So when you look at this, you say it's a polytree. The largest number of parents per node is 2. I can tell you exactly the tree width is 2. You should be able to predict these. Now, these are harder. You can't actually easily tell why they have tree width of 3, but again, we're getting to this later. We'll show you a method that is better than trying all possible elimination orders. Because one way you can say is, let me try all possible elimination orders and then see the width of each and take the width of the best. No, you don't want to do that. There is something that is better. All right, folks. One more topic here that I want to do. This is very significant, practically, what we're going to show next. You've seen it in some form when we did deseparation. And it is something called pruning technique. What does that mean? You want to do inference. You have the network. I come and ask you a question. Query. Remember, what is a query? Marginal over some variables given some evidence. And I'm going to show you now a technique where you would look and say, wait a minute, before I start, if that's the question you're asking, I will prune the network. I will throw parts of it while guaranteeing you that the simplified network will be as good as the original one in terms of answering that question. And the effect of pruning could be substantial, as you will see. And I'll tell you right now, that's also a legitimate and fun thing to ask you about on exams. Why? Because of the connection that I'm going to show you, you will be able to design easy queries. You can say, yeah, this network has a tree width 70. So variable elimination will die on it. But look, I know what's going on here. So here's a question. If you ask on that particular network, you can do efficiently. Why? Because of the pruning, you're going to get a simpler graph whose tree width is going to be 7. See the significance of this? And what makes it even more attractive is how simple it is. So let's do it together. Here's the first part of it. Pruning nodes. Given a Bayesian network, N, and a query, QE. Remember, marginal over Q, the evidence, small e. What you can do? You can remove any leaf node with its CPT from the network as long as it does not belong to this set of variables. It's not in Q and it's not in E, yet not affect the ability of the network to answer the query correctly. Do you understand it procedurally? It's very simple. Any leaf node that does not appear in the evidence variables or the query variables, drop it. Okay, now I want to ask you a question. Prove it. Yes. You have a leaf. I'm saying it doesn't belong to the evidence or the query, throw it out. Say, no, I want to throw it out. I want to eliminate that variable first. What do you do to eliminate that variable first? You look up all CPTs that mention that variable, correct? There's only one of them in this case. It's going to be that CPT. You sum out that variable from the CPT. What did I show you? You get the identity factor. You can throw that away. It doesn't, when you throw it in the mix and multiply, it doesn't do anything. That's a proof. This is not a trivial technique, and look how simple the proof is now that we understand the semantics of elimination. Good. Let's look at, and now you'll see why it's fun to ask questions about this observation. Here's a network, right? I come and tell you I want to compute, no evidence. I just want to compute, I want the joint over B and E, right? What can you do in that case? You throw this guy out. What did you get? This. This is good enough. Look what happened. This was multiply connected. This is singly connected. And you can imagine, you can design things where you can make huge difference in tree width before and after. Well, now I'm going further. I say, no, all I want is the marginal over B. What can you do in this case? You can throw this, throw this, throw this out. This is good enough. This network is good enough to compute that joint. Guess the other part. This is what part A of the simplification. There's a part B. Think about this. This appeared before. Where did this appear? When we did deseparation. Remember? In deseparation, I gave you an algorithm for doing deseparation efficiently. And I told you, you can, if you want to find if X is deseparated from Y given Z, you can remove leaf nodes that do not appear in X, Y, Z, right? And reduce the problem of deseparation into a problem of classical connectivity between X and Y. When we did that, we pruned nodes. We did something else there that we also can do here. Any guess? You remove the outgoing edges from observed nodes. So if you have evidence that say A is true, what you can do is you can go to A is true and remove the edges that are outgoing from it. Do you see why intuitively? I know the value of that variable, right? What are the children doing? The children are giving me distribution conditioned on the state of the parents. And it's covering all cases. But no, I know that the parent has this value. Then I don't have to look at all possible combinations. Let's see this. Unfortunately, in this example, I don't have the original network. I just have the pruned one, but I guess you guys can figure it out. Look what's going on here. The evidence is C is false. Remember what this original network looked like? I had an edge from C to E, and I had an edge from C to D. Now, if you look at the CPT for E, how many rows did it have? 4, correct? It said, if C is true, here's the distribution over E. If C is false, here's the distribution. But I'm telling you, I know that C is false. Then what do? I only keep that part of E. I kill this edge, and I say E no longer depends on C. Here's the new distribution on E, which is this guy. Does that make sense? Similarly for this guy. The original CPT was conditioned on B and C, and it had 4 distributions for every possibility of B and C, correct? Now I know C is true, so I'll just pick the 2 of them that correspond to C being false, and that's what's happening here. And then I can do my work on this guy. You can see how this also can reduce the tree width significantly, right? And by the way, this business of take the CPT for D and only select those parts of it that correspond to C being false. If you want to do it nicely, here's the notation using our operations. You take the original CPT, reduce it with respect to C false, and sum out C. You get this guy. So if you want to describe it algebraically, not as an operation, let's close with this notation and terminology. The result of pruning nodes and edges for a network will be called pruning the network given that particular query. And we will denote it by this. Now, here's the interesting part. There is the notion of a tree width, as we discussed, which is a property of a graph, correct? But now when I give you a query, then I can talk about the effective tree width of the Bayesian network with respect to that particular query. And what does that mean? You take the Bayesian network, prune it by removing edges and nodes, and then you compute the tree width of the result. And that is what we will call the effective tree width of Bayesian network. I want to just do one thing quickly, a couple of slides. It's hard to do this variable elimination without mentioning these last 2 slides. And it is about a way to implement variable elimination that makes sense to the point that people use it even when they want to do variable elimination manually, and it has a name. So you need to know the name. And in fact, that name was given by Rina Dechter to this, who was one of the main people together with David Poole. Rina Dechter is at Irvine. David Poole in University of British Columbia. They did most of the work on variable elimination as we discussed it in the 90s. So the variation I'm going to mention is called bucket elimination. Again, a couple of slides, but important. These are all examples in your book. Okay. Let me just mention what bucket elimination is. It's an indexing scheme to manage the elimination process. Remember, when we did the elimination process, I told you, imagine that you have your CPTs on the table. And then I said, we're going to eliminate X. So go find all of the X guys that, or all of the factors that mention X and multiply them, right? Our complexity analysis kind of assumed that that is an easy process, looking for the guys that mention X and multiplying them. You can make it easy by doing this indexing scheme. So what do? You come and say, I want to eliminate the variables in this order. I want to eliminate E first, then B, then C, then D, then A. So you arrange them in what we call buckets like this, right? Here are the factors that I have. Why did they end up sitting in these buckets? Because of this. You start by, you pick a factor, let's say this guy, C given A, correct? You start at the top and you go down. And you put it in the first bucket whose label is mentioned in the factor. So what is this guy, CA? Do I put it in the first bucket? No, because E does not appear. Do I put it in the second one? No. What about C? Yes. I put it here. And so on. So if you look at this guy, why did it end up being there? It just mentions A. When I go down the list, that's the first place I can put it, and so on. Are we good? You list your buckets, you take your factors, you go to the buckets and start dropping them, and then what do? You do elimination by processing buckets in the order. What do you do when you're processing a bucket? Anytime you reach a bucket, let's say bucket B, you're guaranteed that the factors there are all of the factors that mention B. So I just multiply them, sum out B, and then what do? I drop the result in the corresponding bucket. Let's take an example. Process E. What am I going to do in this case? There's only one factor. I just sum out E from it, correct? Where does the guy go, the result? The third one, in C, not in the second one. Because the result, when I sum out E, I get a factor over C. Doesn't go into the second bucket, go into the third. Right? Okay, now I go to the second bucket. That is the B bucket. I multiply the two factors and sum out B. What do I get? A factor over A, C, D. Where does that go? The C bucket. Right? This is the example. Processing the first bucket leads to this guy, which goes into this, and then you keep going. We're good? Okay, one more trick, which is used in this context, but you can use it more generally. Remember our business of reducing factors? I give you evidence, and I say go to the factors and zero out the rows that conflict with them, right? There's another way to do evidence. And it's practice in this context. I'll show it to you, and then you'll see why it works. Another way of doing this is the following. Here's the evidence. B is true, and E is false, right? The way we did it is you go to every factor. Anytime a row conflicts with this, you zero it out. The alternative approach is this. You just introduce two new factors, this and that are called evidence indicators. So, B is true. You have a factor over B, true, false, and you put 0, 1 to reflect the evidence. See that? Pretty simple. And you do the same guy for E. You good? You take these two guys, what do you do to them? Throw them in the mix. They are cleaners or reducers or zeroers, whatever you want to call them. You can imagine when you take this guy and throw it in the mix of a bunch of factors, what is it going to do? It's going to effectively, when you multiply everything, it's going to zero out every row that mention B false. See that? And similarly, if you take this guy and throw it out into a mix of factors, when you do the multiplication, it will end up zeroing out every row that mention E true. So this is the way you would do evidence in this particular case. And if you're doing it in the context of bucket elimination, to incorporate this evidence, you add this evidence indicator and that evidence indicator in the corresponding buckets, and you just simply perform things as usual. In fact, this is more common. The indicator technique appears in more contexts than what we did. What we did is more effective, but people tend to do this typically. Right? It's not as aggressive. This does the zeroing later in the process. You can try to imagine it. What we did is pretty aggressive. It starts up front and just says, I don't want to deal with these possibilities from minute 0. Right? This guy, if you throw these guys in the mix, you may be doing operations on factors and actually keeping rows that eventually will be zeroed out. You see that? So it's kind of a lazier way of zeroing out. All right. We did a lot today. You're now semi-experts on exact inference. You'll become real experts next time. So I will see you next week. All right. Thank you.